very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be going through the tutorial for week 4. So let's get started. The topics for this week's tutorial are principal values and directions and tensor calculus. We will be solving a total of 6 problems. So let us get started with the problems. So the first problem, as you can see from the tutorial sheet available on the portal, is that we have to show that for 3 distinct eigenvalues of a real symmetric sigma ij, the eigendirections are mutually perpendicular to each other. So let's underline this, that the eigendirections are mutually perpendicular to each other. Now we had stated this as a part of the lecture, and I had mentioned that we'll be discussing this as a problem in the tutorial. So here it is. So the way we start this problem is to first write the eigenvalue problem, that is sigma ij nj is lambda times ni. So these nj's or ni's and these lambdas are the eigendirections and eigenvalues respectively, and as we have 3 distinct eigenvalues, so let us take any 2 of these and write the equation for those 2 specific eigenvalues and directions. So the first one will be written as sigma ij n1j equals lambda 1 n1 I. Let's call this 1. In the second one, we'll write for the direction n2, which becomes lambda 2 times n2I. So the goal here is that we'll take 2 arbitrary directions and show that they are perpendicular to each other, and if that holds, then any 2 directions will be perpendicular because these 2 choices in the beginning are arbitrary. So we'll multiply 1 by n2I. So the idea is that we are trying to make the left hand sides of both 1 and 2 to be the same. So in 1 we have sigma ij n1j, and in 2 we have sigma ij n2j. So we'll multiply equation number 1 somehow by n2 and equation number 2 somehow by n1 and try to make the left hand sides the same. So one must be clear as to what they're trying to do. So this is what we're trying to do here, and then we'll try to use the right hand sides of both and show the relation that n1 and n2 directions are mutually perpendicular. So let's proceed. So when we multiply equation number 1 by n2I, this becomes n2I sigma ij and 1j equals lambda 1 I'll keep on the left just for convenience of writing, and then we have n2I times n1I. So now in the initial notation, it doesn't matter what order we write the different tensorial quantities in a term. I will prefer to write this as sigma ij first, then I will write n1j and then n2I. This is just for convenience to show or visually see that the terms will be the same. The right hand side remains lambda 1 times, I'll write the n1 first again for convenience, I times n2I. So let's call this A. Now let's work with equation 2. In equation 2 we said that we'll multiply this by n1 because we already have an n2 here. So let's do that. So we'll multiply equation number 2 by n1i. So this becomes n1i sigma ij times n2j, that's equal to lambda 2 n1i times n2i. Also note that when we are doing this multiplication, we are doing some sort of a contraction in a sense that the earlier the equations were vectors on both sides, but after multiplying it becomes scalars on both sides. So we are reducing the order, but that's completely allowed. That's again the beauty of indicial notation along with the summation convention. Now let's move the sigma to the left. So this becomes sigma ij times, I'll write the n1 first, n1i, and then we have an n2j equals lambda 2 n1i n2i. And this, well, before I call this b, let us look at the left hand sides, this one and this one. Let's see if we have actually made them the same. So in A, we have sigma ij n1j n2i, whereas in the other equation, we have sigma ij n1i n2j. So n1 has an index j in the A equation and I in the other equation, whereas n2 has different indices. But what we can do here is we can swap the indices I and j because they're both dummy in this expression. So I can actually write this equation as sigma ji n1j n2i. So this is exactly the same because if you expand this and this, they both expand to the same thing because all that's what we have done is we have changed the index names. That's it. But this and this is still not the same on the left hand side because in one we have a sigma ij, in the other we have a sigma ji, although ends have the same indices now. But we also know, if you see the problem and what we're discussing, that it's a real symmetric sigma. Sigma is symmetric, so sigma ij is actually equal to sigma ji. So this actually can be written as sigma ij n1j n2i. This is equal to lambda 2 times n1i times n2i. And this is what we'll call as B. So now we have equations A and B which have the same left hand side. So we can subtract B from A, and this will be a 0 on the left hand side, and the right hand side becomes lambda 1 minus lambda 2 times n1i times n2i. So let's see what we have got. We have a quantity lambda 1 minus lambda 2, which is just a scalar, but it was given to us that the lambdas are distinct. So what that means is that this is non-zero. So if a product of two quantities, well, two scalars, because n1i, n2i is also a scalar, is 0 and one of them is non-zero, then that means that n1i times n2i is a 0, which in the symbolic notation basically means the dot product of the vectors n1 and n2 is 0. And this basically means that n1 is perpendicular to the vector n2. And remember in the beginning we took two arbitrary directions n1 and n2. So this means that since 1 and 2 were arbitrary, all eigendirections are mutually perpendicular to each other. I mean, you can start with n2 and n3 or n1 and n3 and you'll get the same result. So that completes the solution. So the key to solving problems like this is to see the expressions. So if you go back to the beginning, if we look at equations 1 and 2, on the right hand side, we can see that if I multiply equation number 1 by n2i, that's a dot product of vectors n1 and n2. And we have to show that to be 0. That's the aim. We had to show that these two are perpendicular. And then on the left, we see that if I multiply the first equation by n2 with some index, then the left hand sides of the both will be the same. So this is the trick that one has to see the equations first and figure out what exactly has to be shown and then what has to be done to show that. Again, this comes with experience and practice. So eventually you will get comfortable with showing expressions like this. So let's move on to the second problem, which says that we have to write the eigendirections n hats of some second order real symmetric tensor sigma in the principal axes of sigma. So we should mention that sigma is real valued and symmetric. So let's solve this problem. Now for this, one must draw the axes, which are the base coordinate axes and the principal axes. So let's draw that first. So this is the base coordinate axis. So OX1, X2, X3. And then the starred or the principal axes are given as this. Now if I was to write the unit vectors, so in the base coordinate system, these are given as E1 hat, E2 hat and E3 hat. Now what about the starred or the principal axes? So here the unit vectors are actually n1, n2 and n3 hat, because these are the eigendirections which are used to define the principal coordinate system. So if I want to write n1 hat in the principal coordinate system, it's very straightforward, because n1 hat in the principal coordinate system is simply 1, 0, 0, because this is one of the coordinate directions. So I should say in OX1 star, X2 star and X3 star. Similarly, N2 hat is the second coordinate direction. So that's 0 times N1 hat plus 1 times N2 hat plus 0 times N3 hat. Similarly, N3 hat is 0, 0, 1. It's a very straightforward problem. So that completes the solution to problem number 2. The problem 3 says that if a real valued symmetric second order tensor sigma has the eigenvalues lambda and eigenvectors n hat, we have to show that the principal values of sigma inverse are 1 by lambdas and its principal directions are the same n hats. So this requires us to relate the principal values and directions of sigma with sigma inverse. So let us solve the problem. So first I need to tell you that sigma and sigma inverse are related in such a way so that sigma dotted with a sigma inverse is an identity, or in the initial notation this can be written as sigma ij sigma inverse jk is a delta ik, or the other way around I can write sigma inverse ij times sigma jk is a delta ik. So we will start by writing the eigenvalue problem for sigma. because we know that lambda and n hats are the eigenvalues and eigendirections of sigma. So the eigenvalue problem is sigma ij nj equals lambda times ni. The question is, how do we relate this or use these with this? Well, I can pre-multiply the eigenvalue problem by sigma inverse. So to do multiplication, I must do it in such a way that I have the second index of sigma inverse has to be I, so that I can multiply that by sigma ij, so that I can see the multiplication of matrices, and this is an nj, and so let's call this indices as p and I, and on the right hand side then we have lambda times sigma inverse pi times ni. So see, I can write the sigma inverse anywhere here or here, doesn't matter, because in initial notation the order of the terms does not matter here. The indices order matter, but I'm writing it in such a way to see the multiplication of indices. So I'm trying to pre-multiply the equation because I want to write sigma inverse times sigma as an identity. So I'll say pre-multiply by sigma inverse. So this is what we get. So this becomes an identity from the definition of sigma inverse. So this can be written as a delta Pj Nj equals lambda times sigma inverse Pi Ni. So we now write it in this way, that this term goes to the left, and you'll see why. So this becomes lambda times sigma inverse Pi times Ni equals, and then the right hand side is delta Pjnj, which is basically Np. And this now looks like the eigenvalue problem for sigma inverse, because we have sigma inverse times n, and now I'll move this lambda to the right hand side, so this becomes a 1 by lambda times an np. So let's write this clearly now. So this is sigma inverse pi times ni equals 1 upon lambda times np. In the symbolic notation, this becomes sigma inverse dot n hat is 1 upon lambda times n hat. So this is the eigenvalue problem for sigma inverse, and we can see that the eigenvalues are 1 by lambdas and eigendirections are simply the same as n hats. So this completes the solution. So problem 4 is more numerical in nature. We have to find the principal values and directions of sigma, which is given as this matrix representation. Now we can see that this is symmetric and this is also real valued. So we expect that the three eigen directions are going to be mutually perpendicular to each other. So let's start solving this problem. So first I write the eigenvalue problem, which says that sigma minus lambda I times n hat is 0. I'm using the symbolic notation this time. And this is only possible, as we showed, that if this matrix is singular or the determinant of sigma minus lambda I is 0. So this can be written as the determinant 5 minus lambda to 0 to 2 minus lambda 0 and 0 0 3 minus lambda is equal to 0. Now we simply need to expand the determinant, get a cubic in lambda and solve it. I'll leave it to you to solve it. And what we'll get from this is, and you should do it yourself, is that the eigenvalues are 3, 6 and 1. I'm calling them 3, 6 and 1 in any order. You can do it in any order you want. But the eigenvalues should be 3, 6 and 1. The next thing to do is to find the eigendirections. So let's do that. So to get the eigendirections, we have to write sigma times n1 or dotted with n1 is lambda 1 times n1, and we know that lambda 1 is 3, so this becomes a 3 times n1. So this can be written as sigma minus 3 times I times dotted with n hat 1 equals 0. This in the matrix form becomes 2, 2, 0, 2 minus 1, 0 and all three zeros in the last row times n 1, 1, n 1, 2 and n 1, 3, and this is equal to 0. So that's one equation, and you will also require the other equation, which is that n1 is a unit vector. So this becomes n1 dotted with an n1 is a 1. So using this, we can get the n1 vector, and again I will leave it to you to do the work to get vectors n1, n2 and n3, and I'll give you the values for these. So vector n1 is simply 0, 0, plus minus 1. So that's what you'll get. And remember that these are directions, so it can be either in the z direction or the negative z direction. Similarly, n2 hat will be plus minus 2 upon root 5 plus minus 1 upon root 5, 0, and this is n3. So either you can take the signs on the top or signs at the bottom. But please make sure that you visualize the vectors and see that n1 cross n2 is an n3, that is, they form a right-handed coordinate system. If you have n1 and n2, you can cross them and then see that you get n3. So let us move to the next problem. So this is a problem on tensor calculus. It says that for scalar fields lambda and phi, we have to show the following vector identity, which is that the divergence of lambda grad phi is equal to lambda Laplacian phi plus grad lambda dot grad phi. Now with the symbolic notation, it's a bit of a challenge to show this, but with the initial notation, it becomes very straightforward. So what we'll do is we'll start with the left hand side, write this in the initial notation, and then proceed from there. So this quantity divergence of something, if this was a vector u, then we would write this as ui comma I. So this comma I is coming from the divergence, and ui is a vector that is there in brackets. So let's use this idea and write the expression here. So there is this lambda times grad phi is like a vector ui, and then divergence of that gives a comma I. So what is lambda times grad phi? That's lambda, and grad phi is phi comma I. That's what we have seen in the lecture this week. So this is the left hand side in the initial notation. But I can expand this. I can apply the product rule of differentiation. So this becomes lambda phi comma I. So basically you keep lambda and then you differentiate phi comma I, and then in the second case you differentiate lambda and keep phi comma I. So now you see that we are very comfortably using the comma notation without even trying to think of what this denotes in the traditional notation, which is phi comma I would be del by del xi of phi and so on. So let's park ourselves here. Let's look at the right hand side. On the right hand side is lambda times Laplacian of phi plus grad lambda dotted with a grad phi, which in the initial notation becomes lambda times, now Laplacian of phi is phi comma I, as we saw in the lecture, and then grad lambda is lambda comma I dotted with a grad phi. So that means both will have the same indices. So grad phi is phi comma the same index I. So we see now that this is exactly the same as left hand side. So this completes the solution. So you can see that we were very comfortably using initial notation able to show this identity, which using symbolic notation would have been a challenge. So this again is a +1 for initial notation. So let's look at problem 6, which is the last problem for today's tutorial. It says that using the initial notation, we have to show that this integral on the left hand side, which is basically a closed integral over a surface, is equal to 6 times the volume of the object. So we will be using the Gauss's theorem here to relate the closed area integral to the volume integral. So remember, this was a volume omega which had a bounding surface gamma. So let's start with the left hand side. First, we will write this in the initial notation. In fact, the problem says that we have to show this using initial notation. And in any case, using the initial notation is always simpler. So this becomes x dot x is xi times xi. And then you have a grad of that. Now, because xi is a scalar, so the grad of that simply adds a new index comma j to it, because grad of a scalar is a vector, so it has to have one free index. And then this whole quantity is dotted with an n hat. So you have a vector n, but since it's a dot between two vectors, that means that the free index that we had here is to be the index for n as well. So now this quantity here does not have any free index. This is a scalar as expected. And then we have a d gamma. So let's simplify this. So xi comma j using the product rule becomes xi comma j plus xi comma j times xi. It's a symmetric thing, so this is basically just twice of this, and I can remove this, times nj. Now xi comma j is simply a delta ij, as we had shown earlier, because xi comma j is simply del xi by del xj, and xi's are the coordinate directions. So this is a delta ij. So this is twice xi times delta ij times nj. Now delta ij times nj can be written as ni using the substitution property of delta. So I'll do that here, and I'll simply write this as ni. So this is the left hand side, and now we will apply the Gauss's theorem. So let's recall the Gauss's theorem. So the Gauss's theorem said that if you have a surface integral of a quantity, a tensorial quantity of nth order, times nq times d gamma, this becomes a volume integral of the same quantity Cijk dot dot dot, but this time a comma q. You differentiate this quantity with respect to del by del xq times d omega. So So if I try to apply this Gauss's theorem here, so this quantity C is this quantity 2 times xi, this nq is ni. So if you apply that, let's see what we get on the right hand side. So this becomes a volume integral, and then we have the quantity C, which is 2 times xi, and then you differentiate that with respect to q, but this time q is actually equal to I. So we are using a special case, so this becomes I times d omega. So let's expand or open the bracket. So this is 2 times x I comma I. Now what is xi comma I? Well, xi comma I is a delta I. So this becomes a twice delta II integral d omega. Delta II simply is a 3, and 3 times 2 is a 6, and 6 is a constant, so this becomes 6 times integral of d omega, and integral simply of d omega is omega, so this becomes 6 times omega, which is the right hand side. So this completes the solution. So this brings us to the end of this tutorial for week 4. I hope you were able to understand how to solve problems of different kinds on the topics of principal values and directions and tensor calculus. So this also brings us to the end of the first module of the course, that is on foundational mathematics on tensor algebra and calculus. So now we are ready to get into understanding stresses and kinematics. So I'll see you next week with a discussion on stress tensor. Thank you.